Alright guys, welcome back. The skies are opening with thunder in anticipation of this video. So we're going to be talking about how can we do different mathematical operations with series. So we're going to talk about some calculus as well as some algebra. So first off, let's talk about integrals and how we can use series to help us. So one question a lot of people have been curious all year is how can I do this integral? How can I integrate sine of x squared dx? Well, it turns out that even though this looks like a simple integral, it's not very easy at all. Right? You can try u sub, but then the du is not going to work because we don't have an x for that. You could try parts, but you're kind of going to run into the same issue. It turns out this is an integral that we're not able to do by hand. So the way we're going to do this integral is we're going to basically write sine of x squared as a maclaurin series. And then just integrate each term and integrate the general term. So it seems weird, our answer is not going to be a closed function, but we will be able to write our answer as a series, So we can start with sine of x, which of course we're still good students, so like we have that memorized and whatever. X to the fifth over 5. Okay, and then, it alternates and whatever, and it's like the even power terms, and the factorial matches the power. Okay, well, so what that means is when I take sine of x squared, I replace all the x's with x squared. So like in the last video, we have x squared minus x to the 6 over 3 factorial plus, x squared to the 5th power, multiply those, that's x to the 10 over 5 factorial. And then the general term, we have x squared to the 2n plus 1, so we just have to distribute that out. So that is negative 1 to the n times x to the 4n plus 2 divided by 2n plus 1 factorial. Okay, and again, we're just using the general term to start with instead of like trying to come up with our own. Okay, so now that we do that, now we're going to integrate each term. And the good news is that everything is added, right? So if we were to integrate, like x plus x squared minus x to the 5th, you just integrate each term and then add or subtract those. So I'm going to do the same thing here. When I integrate this, I'm going to integrate the whole thing. So if I need to integrate sine of x squared and write that as a series, well, the integral of x squared is like x cubed over 3. The integral of x to the 6, so you could think about that as like 1 over 3 factorial times x to the 6th. So when you integrate, it's like 1 over 3 factorial times x to the 7 over 7. So you just keep that constant that you have on bottom. So we'll have x to the 7 over 7, and then that 3 factorial stays in the bottom. Same thing here. The 1 over 5 factorial is out in front, so it's like x to the 11 over 11, and then you have a 5 factorial on the bottom. Okay, and then as for the general term, just like with derivatives, remember everything with an n in it is just constant. So for my general term here, we'll just have negative 1 to the n over 2n plus 1 factorial. And then if we add 1 to 4n plus 2, we get x to the 4n plus 3, and we divide by 4n plus 3. Okay, now it's not the most beautiful answer in the world, but I think this is kind of cool, right? This is a way that you can actually do an integral of a function that you couldn't integrate before. Yeah, it's a series, but that's still kind of cool. Okay, let's look at one with a definite integral. So with definite integrals, by the way, I should put there's like a plus c on the end here because it's an indefinite integral. But with a definite integral, if you have an integral 0 to x of a series, that's really just an indefinite, but there's no plus c at the end. Now, just a special case if you go to x, but let's do an actual definite integral. So let's say I ask you for the first 3 terms and the general term of the series for the integral from 0 to 1, we'll make our life a little easier, of cosine of x minus 1 over x dx. Okay, so what we're going to do in general is write the series, and then we'll do the integral just like I did on the last problem, and then we'll plug in the bounds of this. Okay, so when I do this, let's go ahead and say, we start with cosine x. Again, we're good students, so we have this all memorized. So we have x to the 4 over 4 factorial minus x to the 6. Okay, so we know it's like alternating, and then it's like the odd or the even power term, and the factorial matches. Make sure you put the 2n in parentheses, so it's not like 2 times n factorial. Anyway, so when I do cosine of x minus 1, so we've talked in the last video, we just subtract a 1 off. It doesn't affect any other terms, doesn't affect the general term. Okay, so everything else is going to kind of be the same. And now, at this stage, again, general terms the same. Now we're going to go ahead and divide this by an x. So now I divide this by x, so I divide all these terms by x as well. So when I do cosine of x minus 1 over x, okay, so each term's over x. This is over x, so we cancel 1, so that's like negative x over 2 factorial plus x cubed over 4 factorial minus x to the fifth over 6 factorial, sorry. In the general term, if I just subtract an x off, we have x to the 2n minus 1. We subtract exponents if we're dividing them. Okay, so now when I integrate this guy, I'm going to integrate, and then my last step will be to plug in the bounds. So now let's go ahead and integrate this from 0 to 1. So I'm going to integrate the whole thing, and then I'll plug in 0 to 1. So when I integrate these terms, again, the negative 1 over 2 factorial is a constant. So it's like negative 1 over 2 factorial times x squared over 2. Plus, 1 over 4 factorial times x to the 4 over 4. And then minus 1 over 6 factorial x to the 6 over 6. You can combine those into 1, of course, if you want. So the same thing here. On the general term, this all is constant. So negative 1 to the n over 2n factorial. And then 2n minus 1, so I'll add 1 to the exponent. So I'll get x to the 2n, and I'll divide by 2n. Okay, so that's my integral. And now when I want to go ahead and I'm going to plug in my bounds. Okay, so when I plug in, I'm plugging in x equals 1 first. So when I plug that in, I'll get negative 1 over 2 factorial times 1/2. And then plus 1 over 4 factorial. Okay, when I plug in 1, obviously that's easy, so just times 4. And then the next one will be minus 1 times 1 over 6 factorial times 6. And then my general term, when I plug in x equals 1 into this term, I'm going to get negative 1 to the n times 1 over 2n factorial times 2n. So again, I'm just plugging in x equals 1 into this term. Okay, and now, of course, when you plug in 0, so this all was what happens when we plug in 1. If you plug in 0, the great thing is every term has an x, so every term is just 0, right? All these terms have an x in it, so plugging 0 does nothing. So it's a little messy, but again, this is our integral from 0 to 1 of this function, which we're just writing kind of as a series there. Okay, that's pretty cool. Let's talk about some other things. Let's talk about limits. So let's say you have to find the limit as x goes to 0 of the sine of x minus x divided by x cubed. Now, you could use L'Hopital. You could use L'Hopital on something like this. Actually, you know what? Let's make our life a little saucier. Let's turn this into x minus the sine of x. Okay, you could L'Hopital it 3 times, but man, like L'Hopital's rule, the hospitals have been pretty busy lately. Let's kind of give them a little break. So let's try and do this limit with a series. Now, again, normally you might want to use L'Hopital's, but occasionally you're going to find one that's like for example, there was one on the AP test a couple years ago that looked like this, where you would have had to use L'Hopital's rule, I think 6 times, and even then it turned out really, really ugly, because you have to use a bunch of chain rules on this product rules. It's just a disaster. So L'Hopital's rule can be really bad in that case. But we're going to do this with series. And again, we're going to kind of do the same strategy. We're going to write this as a series, and then we're going to simplify that out. And then we're just going to plug in and find the limit. And because you're kind of plugging in x equals 0, it's going to make your life pretty easy. All right. So let's start with this. We haven't subtracted the sine x, but x minus sine of x. If we think about that, that's x minus, and then the series for sine of x is it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial and so forth. Okay. So when you do x minuses, we definitely have to distribute that negative out to every term. So x minus sine of x is basically x minus x cancels, and then we have a plus x cubed over 3 factorial minus x to the 5th over 5 factorial plus x to the 7 over 7 factorial and so forth. Okay, and then we're trying to write this as a series. The next thing we're going to do is divide each of these by x cubed. So divide each term by x cubed. So we're going to get x minus sine of x over x cubed equals, okay, so dividing that out, the x cubes cancel. Here we subtract the power, we get x squared over 5 factorial. Here we get x to the 4 over 7 factorial, and so on. Now that I've written the inside as a series, now I'm going to take the limit as x goes to 0. But the beauty is there's no real magic tricks here. You're just kind of plugging in x equals 0. So when you plug in 0, look what's going to happen. The first one becomes 1 over 3 factorial, and then you get minus 0 plus, and every other term has an x. So when you plug in x equals 0, every other term is going to 0. So the only term that didn't end up being 0 is 1 over 3 factorial, or 1/6, if you will. Okay, beautiful. So that's how you can use series to help you find a limit that's a little gnarly. In some situations, it really does save you a lot of time. Okay, let's talk about a couple other math operations. Let's talk about adding and subtracting series. Okay, so let's say we have to write the first 4 non-zero terms of the series, the maclaurin series, let's say for e to the x plus cosine of x. Okay, so let's go back and first off, and notice that I didn't ask about the general term because that's like incredibly difficult on these kind of problems. But let's think about how we add polynomials back in Algebra 1. So if you have these and you had 2x squared minus 3x minus 5, it's not like anything crazy. You just kind of use like terms. You line them up one on top of each other and add down. So that's 3x squared. This is 4x. That's -1. You just kind of add down and nothing crazy happens. So that's what I'm going to do here. I'm just going to line them up and then just going to add together like terms because that's the only way we add polynomials. And what's a Taylor series but an infinite polynomial? So if I have e to the x and then I have cosine x. So e to the x, we know what that looks like. So that's like, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4 over 4 factorial, and so forth, okay? And then my cosine x, that's like a 1, and then minus x squared over 2 factorial plus x to the 4 over 4 factorial. Okay, so let's add these together then. As we add these down, 1 plus 1 will give me 2. That's a tough one. Okay, the x carries down. It's not added to anything. These cancel. That's pretty cute. Plus x cubed over 3 factorial. Okay, now when you're adding these, so when you do x to the 4 over 4 factorial plus x to the 4 over 4 factorial, if it's the exact same, it's just like 2x to the 4 over 4 factorial. But you can also just like factor it out, right? So this is x to the 4th times 1 over 4 factorial plus 1 over 4 factorial. And you can really just honestly like leave your answer like that if you want to show kind of where it comes from. Like that's your coefficient of the whole thing. Okay, and that's again you adding these two terms. So those are the first 4 terms of that series when you add them together. And subtracting will be the same, but of course you just need to distribute a negative. The only other thing I wanted to do is to talk about how do we multiply series. Okay. Now, and again, let's go back to Algebra 1. If I do x plus 3 times, I don't know, like 2x squared minus 5, what do? Well, you just FOIL everything out, right? You FOIL and you multiply every term by every other term. And with series, it's no different. So we're just going to write the terms up to x cubed. This is what's called a third degree Taylor series, third degree maclaurin series. So write the terms up to x cubed of e to the x times cosine of x. Okay, so what we're going to do is we're just going to kind of FOIL out the series. And we're going to FOIL out each term until we are bigger than x cubed. So until we get bigger than x cubed, we're just going to keep FOILing. Okay, and then once we do that, then just like normal, then we're going to combine our like terms as we always do. Okay, so when I have like e to the x times cosine x, let's just write out the terms up to x cubed. So e to the x is like, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, okay? And then when I want to do cosine x, it's just 1 minus x squared over 2 factorial, and then so forth. Okay, so let's go ahead and multiply these out. So it's going to seem like a lot of work, but I'm going to line the terms up right. I'm going to have like, here are my constants, here are my x terms, here are my x squared terms, my x cubed terms, and everything after that we don't care about because you say we're only going up to x cubed. It may look intimidating to multiply infinite terms by infinite terms, but it's not actually that bad because you're just doing like terms. Okay, so you multiply 1 by 1. I think that's 1. Okay, 1 times negative x squared over 2 factorial, of course, is negative x squared over 2 factorial. Let's do the next one. When I multiply the x times 1, of course, is x. So I'm going to put an x in this column. X times negative x squared, so that's a negative x cubed over a 2 factorial. When I multiply the x squared over 2 times 1 is, let's see, that's an x squared over 2. Oh, that's sweet. All right, and then when I multiply the x squared times the x squared, that would give me an x to the 4, so I'm not even worried about it. All right, and then finally I multiply the x cubed over 3 factorial times 1, so I'll add that in, so plus x cubed over 3 factorial. All right, so those are all the terms I got, and now I'm just going to combine together my like terms. If you just want to like write them out in a line and then combine them, that's fine too. So I have a 1, I have an x, but I need to make sure they're kind of like one individual term. So then these cancel there. And then for my x cubed terms, on my coefficient there, I have a negative 1 over 2 factorial plus a 1 over 3 factorial for my coefficient. Okay, so it's a little messy, but that's how we multiply things out, like two series, like an e to the x times a cosine x. Just do the FOIL, just with a lot of terms, and then just combine the like terms and put them together. Okay, so this video is about working with these Maclaurin series. I hope this was helpful, and make sure you bring me questions to class. I'll see you all soon.